Hello, welcome to the inverse of the gamma function and its numerical evaluation. This is work with Camargos Couto and David Jeffrey. I'm Rob Corless. So I'll begin by saying that this is based on work that I did with John Borwein and published in 2018. And 2019, the paper won a Helmholtz Ford Prize from the Mathematical Association of America, and there's a version of it up on the archive. There is a related video from the Oaxaca meeting that organized by George Laban, and a more recent video on our work on the gamma function can be found at the Isaac Newton Institute program on complex analysis tools and techniques. There's another paper with Lely Raffier-Sevieri on Stirling's original formula, which has appeared in Experimental Mathematics. Then there's the master's thesis by Amenyo Folitse. This talk, however, is about the work with Anna Camargos Couto and David Jeffrey on the complex branches. All I'll have time to talk about today is actually the starting guesses for numerical evaluation, which are the same for real as complex branches. So I'm going to talk as if I'm working only in the real plane. So begin with a fact about the gamma function. The gamma function is something that interpolates the factorial. Gamma of z is z minus 1 factorial. And that the two different notations for the same function is actually due to Euler. People blame other people for the gamma notation, but it was in fact Euler as well as the factorial notation. But too late. We have to deal with both of those. It's a minor but continual nuisance. So I'm going to skip over the introduction about the gamma function, but it's present in the Maple worksheet that will be shared with this talk. And there's some discussion about the other articles in the article in the monthly, and I particularly want to mention the Chauvenet Prize-winning paper by Philip J. Davis, published in 1959, and also a paper by Menjul Bhargava, the Fields medalist. So there's some very interesting things to read in the American Mathematical Monthly about gamma function. There's a million facts about the gamma function and Stirling's original formula and our theorem, and I'm just going to skip over that, and I want to give you how to compute the inverse of the functional inverse, not the reciprocal, the functional inverse of the gamma function in the complex plane. Here's a picture of that, of that function done by Newton's method. You get a Newton fractal. And this Newton fractal was produced by Stephen Thornton. And I just love the picture, and I hope you do too. Anyway, if you ask Maple to solve gamma of y equals x, it says, sure, no problem. That's root of x minus gamma of underscore z. And for many purposes, root of really does give you an inverse. If you plot it, well, that now works. It didn't used to work. You used to crash Maple. But it now works, but you only get one branch, and really only part of one branch. So it's kind of strange that it does that. So let's look at the real branches of the inverse gamma function. First, let's look at gamma itself. Here's a plot of the gamma function from the interval x going from -6 to 4, and the view going from -4 to 6. So you get a nice picture of the gamma function. And quite clearly, we have singularities. We have a pole at 0, another one at -1, another one at -2, another one at -3, and so on. But there's the gamma function, so we have pole. And the main thing is that this is a true function. So given a value of x, there's only one value of y, at least in terms of real values. But in fact, that's the way it is. The reciprocal gamma function is entire. But let's look at the functional inverse of gamma. So to do that in Maple, we just interchange in a parametric plot x and y. So here we plot the functional inverse. And you see that it's perfectly easy to draw in Maple, and we have multiple branches. There is the only branch that was drawn by the root of, by the way, but we have all of these other branches to deal with. the location of the branch points, the places where these change, is subject to analysis, and I'll show you a formula for that in a little bit. If we just zoom in on that one branch in the positive plane, so this is the branch that goes off to infinity, and here is another branch which says that when x equals 4, for instance, there are going to be two values of the inverse gamma function, two real positive values of the inverse gamma function, one there and one there. Okay, well, how do we deal with that? It turns out that Stirling original series that I talked to you about, that I glossed over completely, can be inverted. So we can invert Stirling's original series, although not the series that we all know as Stirling series. That's due to de Moivre. One of the funnier things in modern mathematics is that this original series by Stirling is now becoming known as de Moivre series, so that they've traded back and forth. But that's okay. I'm perfectly happy with that. If we solve the Stirling's original series approximation of the gamma function, then we get an answer in terms of Lambert W. And see David Jeffrey's talk in this conference on simplifying Lambert W, but also do help on Lambert W in Maple to find out what that is. But Lambert W is known to Maple. Quite a lot of the properties of Lambert W are known, and in particular, it can be plotted. So if we simplify that a little bit, this answer, we get 1/2 plus log of something divided by Lambert W of log of the same thing divided by E. And that is our approximation to the inverse gamma function in the positive quadrant. Now, Lambert W has two real branches, the 0th branch and the -1 branch. So we'll plot both of those two things on the same graph. And we get the red one from the 0th branch, and it's an asymptotic series. So it's supposed to be really, really good for large X, but it's amazingly good. It actually comes around and pretty close to locates the branch point. And then the blue dashed one is the Lambert W -1. It's actually managed to turn the corner of the branch point. And this is from an asymptotic series that's valid only at infinity. So this is just an astonishingly accurate approximation to the functional inverse of gamma in the first quadrant. So we can actually regard that as being pretty much solved in there, because with that initial guess, we can use Newton's method with no trouble at all to find the inverse gamma. Just to be perfectly clear about it, there is the formula for the approximation to the functional inverse of gamma in the right half plane. If we plot the residual, we see the residual goes to 0 slowly, but it goes to 0 as x goes to infinity. So you can see the master's thesis of Emmanuel Follotzi at the Western Library repository for more details on that. There's some connections to the complementary error function, but everything with a star on this worksheet I'm going to skip over. So now what about the other branches? How do we deal with the other branches? Well, one thing is to look at the series for the reciprocal gamma near negative integers and revert those series. And those will give us a bunch of approximations valid near the poles, well, the flipped over poles, the horizontal poles, of the reciprocal, the functional inverse of gamma. So it's hard to keep track of reciprocals and functional inverse in the same thing, but trust us, this actually works very, very nicely. This works as well as we could. Maybe I can increase the size of this a little bit. So we'll work to fourth order. What we're going to do is we're going to start with W is 1 over gamma of Z. And I'm going to take the series in terms of Z near Z equals a negative integer. So why W is 1 over gamma is because gamma of Z is 1 over W, because W is 1 over Y. So we put in a reciprocation in order to help things out. If we do the series near Z equals minus N, where N is assumed to be a positive integer, so we've got a minus N in there, I think it's astounding that Maple knows the Taylor series for symbolic integers N. So this is just an amazing result that we get the series up to this order. This can be derived from a series of Bourguet in 1883, but there's some work involved in this. So this is pretty impressive. So we get 0 is equal to this series in terms of Z plus N, minus W. So now we can solve a series equal to 0, and we solve it for Z, and the result is we get the reversed series. This is a trick for reversion of series that a large number of people do not actually are not aware of. And of course, reversion of series is something that could be taught in first year calculus, but just isn't. You might get taught it in a combinatorics class where you get taught about the Lagrange inversion formula, but it's just a fabulous way of getting reversed series in Maple. Just solve a series equal to 0 for one of the variables. And out pops Z is equal to minus N plus minus 1 to the minus 1 gamma of 1 plus N times W plus something times W squared plus blah, blah, blah. We can simplify that a little bit. So we simplify that and cleans it up a little bit. And I prefer seeing it in terms of factorials. So might seem perverse of me to want a series for the functional inverse of gamma in terms of factorials, but seeing factorial reminds me that these things are integers. So N here is a positive integer. And we have the series Z is equal to minus N plus minus 1 to the N over N factorial times W plus blah times W squared. Look at that N factorial in the bottom here, N factorial squared in the bottom here, N factorial cubed in the bottom here. This series converges like a bomb. So if we evaluate that now with W equals 1 over Y, we have minus N plus minus 1 over N factorial times Y factorial, blah, 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 blah. And this solves Y equals gamma of Z for Z equals inverse gamma of Y when Y is not 0, but Z is near to a negative integer. So these will give us values of the inverse gamma function when Z is near to a negative integer. So this will be useful near those horizontal singularities. But that's not enough. We actually need to be careful about distinguishing one branch from another. So we're going to have to take the series about the branch points. So taking the series about the branch points is a little bit more difficult. The places where the derivative of gamma, that is psi of Z, is 0, will give us the location of the branch points. These are all real, and that's true. There are no complex branch points for the functional inverse of gamma. These are all real with only one positive branch point between 1 and 2, and an infinite number of negative ones. And the nth one is between minus N and minus N plus 1. So, for example, if we look for a 0 of psi of Z between near to minus 13, in fact, we pick the term plus 1 over log 13, we get minus 12.71, and away we go. So if minus 13 plus 1 over log 13 is about minus 12.6, and the 0 of the 12th of the psi function near that is minus 12.71. So that's actually a pretty good approximation. It gets to be a better approximation for larger n. These are typically denoted alpha 0 for the positive one, alpha 1 for the first negative one, alpha 2 for the second negative one, and so on. Hermite knew that these things were asymptotically the kth one was minus k plus arctan pi over log k over pi plus higher order terms. The asymptotic series is very slow, and I disagree with the next terms in some of the literature. But here's what the next terms look like here. Neither asymptote nor multi-series asymptote can or will, without forcing, give you more terms in the asymptotics of arctan of pi over log k. But the series of arctan for small x gives you the next few terms. So the pi over 1 over pi times arctan of pi over log k is asymptotic to 1 over log k minus these things. So you can see that that's, it going to 0 as k goes to infinity, but rather slowly. Logarithmic growth is rather slow. But we skip over all of these numbers here, which are just checking those next terms. And I think I have a proof for this as being the next order. Let's skip all over those and just look at how well it performs. So here are the locations of the turning points done in terms of inverse gamma. And now we want to take series of inverse gamma about those points. So we're going to have branches. One series is going to have to go up and one series is going to have to go down. Well, how do we do that? If you plug in alpha is root of psi of z, then this generically represents all of them. We take the series for gamma about z equals alpha. All right, there we know that that term is going to be 0. So when we do a solving of this series, we're going to get a branch point series out of it. So simplify gets rid of that next thing. If you ask Maple to solve, it says, no, I can't do that. And part of that is the fact that we've just got the root of in there, and it doesn't really know what to do with the root of. If we replace the alpha with a symbol and then do a series and reverse the series, we correctly get these branch point series with square roots in them. And if we do that, we get both branch point solutions. With those branch point solutions, we can then start Newton's method to get the correct value of the inverse gamma for the branch that we want. I'm not going to talk about the Riemann surface or about collecting these things. Instead, I'm just going to end the talk. This work was supported by NSERC and by the University of Western Ontario. And also, we thank Emmanuel Folozzi and Lely Raffier-Sevieri for their help. And thank you for your attention.